Today I'm going to solve one numerical method in chemical engineering problem. So now here is the problem 4.21. Find the molar flow rates of all pieces out of an equilibrium from the reactor when the inlet values of nitrogen, hydrogen, ammonia are given. So that is 1.1, 3 and 0.2. The equilibrium constant is given 0.05 and at 589 Kelvin, and this equilibrium constant Kp is equal to mole fraction of ammonia divided by mole fraction of nitrogen to the power half, mole fraction of hydrogen to the power 3/2 into 1 by P. For the reaction written as half of nitrogen plus 3/2 hydrogen, and that will produce, that is reversible reaction, ammonia. Use 220 means 220 atm for the pressure. First one use MATLAB and then use Excel. Means by using here I'm solving this problem by using MATLAB, and then later I'll again post another video, so that video I'll solve the same problem by using Excel. Now here I'm doing that things by using MATLAB. I'm solving that problem. For that, so I have to formulate the problem and then I'll solve and then I'll show you what is the answer. Now here, let x mole of ammonia produced and reach equilibrium. Okay, so here reaction is given by stoichiometric reaction is given by half of nitrogen plus 3/2 hydrogen, that will produce ammonia, 1 mole of ammonia. Now from this stoichiometry we know, from this stoichiometry, this equation, we can say that 1 mole of ammonia production required half mole of nitrogen and 3/2 mole hydrogen. Now here I am considering the x mole ammonia is produced. So x mole ammonia production required x/2 moles of nitrogen and 3x/2 moles of hydrogen, and I am saying that let x mole of ammonia produce and reach equilibrium. Now at the equilibrium, what will be the nitrogen, what will be the hydrogen, and what will be the ammonia, that I am going to calculate here. So now in this table, the nitrogen, hydrogen and ammonia is already there, and inlet molar flow rate in that question, that is 1.1, 3 and 0.2, total is 4.3. Now molar flow rate at equilibrium. So at equilibrium, how much nitrogen is present? So initially that was nitrogen was 1.1. now x/2 moles nitrogen required for x mole of ammonia, so means x/2 is consumption, so remaining will be the at equilibrium, that is 1.1 minus x/2. Similarly hydrogen, initially it was 3 and now consumption is 3/x/2. Now present at equilibrium, 3 minus 3/x/2 is there. Now how much ammonia will be there? So initially it was 0.2, now x mole ammonia produced, generation, so total will be 0.2 plus x. Now if I add all this, so total molar flow rate at equilibrium, so that is 4.3 minus x. Now at equilibrium, what will be the mole fraction? So we know mole fraction is individual mole by total mole. Now here total mole is, this is total mole, and individual mole is here. Now so mole fraction of nitrogen, so that is 1/1 minus x/2 individual mole by total mole, 4.3 minus x. Similarly for hydrogen, 3 minus 3x/2, 4.3 minus x. Similarly for ammonia, 0.2 plus x, 4.3 minus x. Now if you add all this mole fraction, you know summation of all mole fraction is 1, so you will get same thing. Now we know mole fraction. Now data given, P is given, that is 220 atm, okay, and Kp value is given. Now mole fraction we know, ammonia, nitrogen and hydrogen, and expression of equilibrium constant is also we know, that is given in that question. So Kp is equal to mole fraction of ammonia y mole fraction of nitrogen to the power half, mole fraction of hydrogen to the power 3/2 into 1 by P. Now plugging all this value and expression become, so if we plugging mole fraction ammonia, nitrogen and hydrogen, so that will be here, and Kp is equal to that total plugging value into 1 by P. Now we know Kp value and P value. Now if we plug this value, 0.05 is equal to this total things, and then 1/220. Now if we simplify, then we will get this equation. So 0.05 into 220 in this, and then again if we simplify and if we everything take in the left hand side, so f of x is equal, so 0.05 into 220 in that numerator, 0.2 plus x into 4.3 into x, and 1.1 minus x by 2 to the power half, 3 minus 3x by 2, 3 by 2. So that is the equation that will become 0. So it is a non-linear equation. Now we have to solve this x, and that x will means this is the non-linear equation, this is non-linear equation, and we have to solve to find out the root of this equation. Okay, so if we get the root of the equation, so that will be the x mole of ammonia actually produced, okay, at equilibrium, so that we can calculate, and then rest of the things, rest of the mole fraction at equilibrium, we can calculate that. Now how do you solve this problem? So now you can solve many ways. You can use Newton-Raphson method, you can use bisection method, many other method. Now here, so I'm going to solve by using MATLAB. So fx is equal to, that is the equation. Now using f0 function in MATLAB, we can easily solve the root of the equation. F0 means, in f0 means you have to find out, means by using MATLAB will find out x value, so that if we put that x value, that function becomes 0. So that is that function f0, we can use that. So for that, so we have to write that f, how do you write in MATLAB? So that is given, and then so this is the first declare the function. Okay, so function is f is at the rate x, this is the total equation we have to write in MATLAB. Then root will be is equal to f0, then calling the function and initial guess, this is initial guess, and then display root. Okay, so now here I am giving the that MATLAB code, so that is MATLAB, or we can write MATLAB code, okay, so you can type and you can run this code and you will get the answer. So here root is the root of the equation is 1.4691, and then molar flow rate at the equilibrium, so I am using that in nitrogen is equal to 1.1 minus x by 2. So here x is root, x is nothing but root. Okay, so x by 2, if we do that, we'll get that molar flow rate at the equilibrium, so nitrogen, hydrogen and NH3. So now total will be 2.8309, and then mole fraction we can calculate. So y of NH3 individual mole by total mole, so here then nitrogen by total and hydrogen by total and ammonia by total, so here we can easily get the mole fraction. So mole fraction is here, and if we sum that mole fraction is 1. So I think our solution is correct, I think so, because we are getting 1. Now so x is 1.4691 moles of ammonia produced and reach equilibrium. So now what will be the molar flow rate and mole fraction at the equilibrium? So component is nitrogen, hydrogen and ammonia. Initially we have 1.13 and 0.2, it was 1.13, 0.2 and total 4.3. so molar flow rate at equilibrium, so we got the x value, so we'll get that. So that is 0.3654, 0.7963, and then nitrogen is 1.6691, so total is 2.8309. and then if we calculate mole fraction is individual by total mole, so that is mole fraction of nitrogen is 0.1291, and hydrogen is 0.2813, and mole fraction of ammonia is 0.5896, and total if we add that, so that is 1. So that is the answer, what will be the molar flow rate at equilibrium, as well as we can also calculate molar flow rate or mole fraction at equilibrium. So I think that's it. If you have any question, you can put your comments, and you can watch this video again and again through this YouTube channel. Okay, and share your comments, thoughts. So if you have any issue, any problem, you can do that. Thank you.